Okay, today we will do electrostatic force due to continuous charge distribution. So in this case we will have three parts. The first part is linear charge distribution, the second part is surface charge distribution, and the third part is volume distribution of charge. Now let us start with the first part, that is linear charge distribution. Linear charge distribution. So here that means the charge are distribute over a long conductor, for example a long thin wire. So let us consider a very thin conductor of length L. This is a thin conductor of long thin conductor of length L with a uniform positive linear charge density lambda coulomb per meter. Okay, so here it is positively charged, which distribute uniformly. Now in order to find the force F on a test charge Q naught placed at point P, so let us say this is the charge Q naught placed at point P here. Okay, we shall use the technique of calculus. Now we consider a very small length dl here. Let us consider a small length dl here on the conductor, and then let us say this, the position vector between L and this point here is R. Position vector is R to here. Now we let us say the small amount of charge, because let us say the small amount of charge dq, because of this small element here dl is given by dq, which is equal to lambda dl. Okay, so then we can say the force df, let us write it, the force df on Q naught due to this charge element, here dl, so is given by df, which is equal to 1 by 4 pi epsilon naught Q naught lambda dl by r square r cap. So here you see, if we consider this charge element here, they are behaving like one of the charge. So another charge is the test charge Q naught. So it is like a system of two charges. Now we apply Coulomb's law in a system of two charges. We have, like before, we have F is equal to 1 by 4 pi epsilon naught Q1 Q2 by r square. Here also we have dF is equal to 1 by 4 pi epsilon naught. Q naught is one of the charge, lambda dl is another charge, so Q naught lambda dl by r square r cap. Now the total force F on Q naught due to the whole length, can be found by integrating the above expression over the whole length L. Okay, so therefore we can write here total force on Q naught given by f, let us say f, it is equal to integration over the whole length L, 1 by 4 pi epsilon naught q naught lambda dl by r square r cap. Now, or I can write here f will be equal to q naught is a constant and 4 pi epsilon naught also is a constant. Bring them out. So what is left here is only integration over a length L. So what is left here is only lambda by r square. I can arrange it by r cap dl. Name this as equation number 1, and equation 1 is the required equation. Is the required equation. So equation 1 gives the expression of the force F on the charge Q naught due to a linear charge distribution on a thin conductor of length L. Now let us do the second case, that is surface charge distribution. Case number 2 is surface charge distribution. Surface charge distribution. So here also let us consider a surface S. Okay, so this is a surface S. Let us say this surface S having a positive surface charge density, let us say sigma. So the surface charge density here is sigma Coulomb per meter square. Now it is desired to find the total force F. On a test charge, let us say here Q naught, which is placed at point P, which let us say now to do that we have to consider a small area here. We consider this small area, let us say ds, which is at a position vector r from the charge Q naught, which is at a position vector r from a charge Q naught. Okay, so we have to find the force on charge Q naught due to this small area ds here. So now we know that the small charge dq on this small area here, it is given by dq sigma ds, charge density into the area, so sigma ds. Okay, now the force df, we can write the force df on Q naught due to this charge element is given by df, which is equal to 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught. Then here it will be the one of the charges Q naught, another charge is sigma ds, and r square is the distance, so r cap here. Okay, so therefore we can write here the total force with same procedure like we have done there in the case of linear charges. We integrate it, so total force, let us say F, will be obtained by integration over the whole surface S, 1 by 4 pi epsilon naught Q naught sigma ds by r square r cap. Okay, or we can write here F will be equal to Q naught is a constant, 4 pi epsilon naught is a constant. Now integration over surface S, what is left here? Only sigma by r square, then I write r cap here, then ds. Name this as equation 2, and equation 2 is the required is the required equation. It gives the total, it gives the expression of the force F on the charge Q naught due to a surface charge distribution on a surface S. So equation 2 will give us the total force experienced by the charge Q naught here because of this surface S, total surface S. Now the third one is volume distribution of charge. So let us see volume distribution of charge or volume charge distribution. Number 3, volume distribution of charge. Volume distribution of charge. Now here let us suppose, here also we will consider a volume V. Okay, V, let us say having positive volume charge density, rho, okay, coulomb per meter cube. Let us say charge here, positive charge density. This positive charge is uniformly distributed the whole volume, and so that we will get the charge density as rho coulomb per meter cube. Okay, so it is desired to find the total force F on attached charge Q naught somewhere here, charge Q naught, which is placed at point P. Now we consider a small volume dV here. Let us consider a small volume dV. We consider a small volume dV which is at a position vector r from the charge Q naught. Okay, so now this is having volume dV. Okay, now the small charge dq on this volume will be, the small charge dq on this volume dV will be equal to rho dV, charge density into the volume, rho dV. Then the force dF, similarly like what we have done there, the force dF on Q naught due to this element, charge element, is given by dF, which is equal to 1 by 4 pi epsilon naught. Then here it will be Q naught rho dV divided by r square, r cap. Now the total force, therefore the total force F will be obtained by integrating the whole volume V of this equation. So 1 by 4 pi epsilon naught, integrating over the whole volume V, 1 by 4 pi epsilon naught Q naught rho dV, so by r square, r cap. Okay, so or we can write F will be equal to Q naught is a constant, 4 pi epsilon naught is a constant, then integration over the whole volume V, rho by r square, r cap dV. Name this as equation number 3. So equation 3 is the required equation. Equation 3 is the required equation. It gives the expression of the force F on a charge Q0 due to a volume charge distribution on the volume V. So with this we complete the topic today. Thank you.